Thanks. Yeah, thanks for having me. So I want to talk a little bit about a project I've been working on for about a year called Rust Lightning. I started it, I guess, December, so a year and a few months ago. And I guess this is kind of my first presentation on it, so I'm kind of excited to finally get to talk about it a little bit. So it is yet another Lightning implementation, because somehow we needed another one, I guess, or really not. But about a year and change ago, I decided, OK, I want to learn Rust. Everyone's super excited about Rust. What is this thing? Maybe there's something here to it. I also wanted to learn a little bit about Lightning. We didn't have anyone at Chain Code who had worked on any Lightning things. I wanted to kind of get into the meat of it a little bit, because we were just kind of a Bitcoin core shop, and we're a research lab, so it's nice to have people who know all of the different pieces. And I kind of figured, look, there's the spec thing here, but most of the implementations have been done by working with each other. And it'd be nice to have something that's done completely clean room, just from the spec, just to see how good the spec is, to improve it, to provide feedback, and see what kind of misconceptions I can come up with about how Lightning is supposed to work by just reading the spec without reading any of the other implementations. Turns out there were a number of them. The spec is good, but it could use a little bit. Anyway, so I kind of got started, and I started working on this and writing it, and it was fun, and I learned a lot about Rust and a lot about Lightning. And then I kind of realized there's this little niche in the Lightning node ecosystem that really just isn't filled at all. And that's to not kind of be a wholesale node and provide people flexibility to integrate Lightning in the way they want. Right, so today you can go take C Lightning and you can run it, and it has a great interface and it works. Or you could take LND and you can run it and you communicate over gRPC. You can take a Claire, and even that has a lot of kind of how it interacts with other peers built in and baked in, and how it manages keys and all of those things. But there's not really a good Lightning implementation that you bring your own key creation, and you figure out how you want the UX to work. You figure out how you want the disk storage to work, exactly how you want all the pieces to fit together. And so that's kind of the niche that I've slipped into trying to fill with this project. So the key kind of, at least initial supported use cases are, first of all, existing wallets, right? So we have this big ecosystem of Bitcoin wallets out there. Most of them don't support Lightning, because how would they have supported Lightning a year ago? And how are they going to go integrate Lightning without starting completely from scratch, getting all of these protocol details correct, and doing just a ton of work to make sure they handle every possible edge case in Lightning correctly? So hopefully Rust Lightning is just kind of this easy thing that you can take off the shelf. You can integrate it tightly with all of your existing management of UTXO and chain state and everything. And you can and then it kind of deals with the rest for you. It deals with channel management and peer management and all of those good things. The other use case that I want to support a little bit better is flexibility around how you do, whether it's a hardware wallet or whether it's like these partially offline nodes. And I'll get into a little bit more of what I mean by that in a minute. But letting people have more kind of high assurance, or at least different security models around how they run their Lightning node, instead of just, I have an online server and I put funds in it and I trust that it's not going to get hacked. So that is kind of where it's gone. And it's made a lot of progress. It's mostly there. There's some stuff I want to change in terms of getting the last bits of on-chain handling implemented. And then I want to wait for some of the 1.1 spec stuff in Lightning before I ship it, because that simplifies a lot of the interfaces for clients, especially around fee handling. So at a high level, what does Rust Lightning look like? So it's completely, there's no runtime, right? So a nice thing about Rust is there's no runtime, there's no background threading, there's no garbage collection, nothing like that. So there's no JVM required. It's not like Go, where you have these threads that need to be started and run garbage collection and all of those kinds of things. And Rust Lightning is entirely event-driven, right? So you call into it, and it doesn't do anything unless you're calling it, right? Because it doesn't have a background thread, so it has to. This means it's embeddable everywhere. If you can compile to LLVM, and you can compile C code to your target, you can run Rust Lightning, hopefully. There's a few more pieces to work out on that, but it's just completely, you can run it anywhere, including hardware wallets, including Wasm, that kind of thing. It's designed to be fairly modular. So especially the different pieces that you might want to have separated or replace on your own. So that means routing. If you want to do your own routing management, you want to do your own routing algorithm, you want to do your own routing table management, it's completely stubbed out. There's a simple interface for it. There's a default one provided that you can use, or you can just build your own, no problem. The channel management is separated from the actual monitoring of the channels, right? So the pieces that have to watch the chain and handle updates to on-chain transactions is separate from the actual management of what the state of all your HTLCs is and what the state of all your channels is. And this lets you very easily take updates from the channels. So the channel manager gives you these updates that says like, hey, I've received new information that you need to make sure to watch the chain for, gives you that blob, and then you can figure out how you want to get that to the device that needs to watch the chain. So maybe you have multiple different devices that are watching the chain, aka watchtowers. Maybe you have the actual channels are managed on a hardware device, and you have a remote watchtower, something like that. This lets you have flexibility there of exactly how you want to integrate these things. So this is kind of pseudo-native watchtower support. Exactly what form watchtowers take is kind of weird because there's a lot of different trade-offs in terms of what data you need to sign in advance and provide the watchtower, how much data it needs to store, versus how much you're trusting the watchtower with respect to privacy and with respect to how much maybe it could steal your funds versus storing a lot of data. There's a lot of trade-offs there. And I think the next talk will cover that a little bit better. Hopefully, most of that goes away with L2 and other future work. But today, it's complicated, so there's not full kind of flexibility on types of watchtower yet in Rust Lightning. But definitely, like kind of if you trust the servers that are watching the chain for you, or you trust the watchtowers, it's very easy to kind of spin up a bunch of different servers doing watchtowers. So disk writing is kind of like all of the kind of system interaction pieces are handled on the client side. So Rust Lightning doesn't figure out how to write stuff to disk. It just hands it to you. And this allows you to have flexibility and say something like, OK, here's an update. You need to go update your watchtowers. And you can say, well, actually, I couldn't get in touch with the watchtower. Please pause that channel. So it has flexibility here. It turns out that's super complicated to get right, and I'll talk about that a little bit more when I go into some of the fun things we've done with testing on Rust Lightning. But the handling of pausing channels for watchtower updates has actually been pretty useful in terms of being able to have flexibility around how you monitor the chain. So I did mention Rust Lightning doesn't do chain sync for you, right? Because a key user of potentially Rust Lightning is existing wallets, and I've spoken to a number of existing wallets who are kind of excited about this idea, but they all already have their own chain sync, right? They're all already SPV clients, or maybe they use Electrum servers or whatever. This is designed to be flexible in Rust Lightning. It gives you all the information you need of like, here's the transactions that you need to watch for, here's exactly the scripts and the TX IDs and whatever, so that you can use Electrum servers, you can use Neutrino, you can use existing Bloom filter stuff. It's all pretty flexible, and you can choose exactly how you want to integrate with the Bitcoin chain. Also, of course, BYO, RNG, and key creation. The goal is that Rust Lightning doesn't make syscalls for you. It just needs malloc. It's not 100% there, but it's getting close. And that means you have to have your own RNG. But of course, if you're doing hardware wallet or something like that, you're going to want to use the hardware features anyway. So I'm not going to try to guess what environment you're running in. You have to kind of plug that in yourself. Finally, the actual TCP handling is up to you as well. There's kind of this easy interface that I've written that looks exactly like select, so you can just map this to an existing TCP socket handler, super simple, or you can consume the messages manually, and this has actually been very useful for testing because we have a ton of test harnesses that deliver messages out of order and delay message processing to simulate speed of light, latency between nodes, which has allowed us to be really flexible in terms of how we test the library. So in terms of the kind of use case of having existing wallets that want to use Rust Lightning, there's kind of a few key elements of how Rust Lightning fits into that. First of all, as I mentioned, hopefully it can live in any runtime. I'm trying not to guess anything about the system you're running on. The goal is that it makes no syscalls except for needs to be able to call malloc, or I guess no libc calls except for malloc. We're not quite there. We currently have some locking calls that we want to be able to stub out, but we're getting close. So malloc, okay, that makes it a little bit harder with hardware wallets, but it's close. It's completely C-callable, right? So you don't need to know anything about Rust. You just need to be able to know how to call a function in C and link a shared library, which every language in the world should be able to do at this point. And finally, Wasm. The goal is to be able to run this completely in a web browser. We're almost there. We need to remove one more dependency, but you can compile Rust Lightning and run a full Lightning node in your web browser. I don't know exactly why you'd want to do this, but in theory, we support this. And at least there's some excitement around running Lightning nodes and extensions. And this will definitely allow you to sync different nodes. So maybe you have your Lightning node, and you just keep an encrypted copy on a server of all the data for the Lightning node. And when you're on your computer, it runs in your little Chrome extension or in your React Native app. And then when you go on your phone, it downloads the latest state, and it stops the one on your computer and runs it on your phone. And it's just the same library that you're running everywhere, and you can just compile it how you like. So in the model of doing kind of hardware or doing kind of more trusted or more high assurance Lightning node, one key goal is to do what I have been calling semi-offline nodes. So they're kind of offline, but in practice have constant updates. So what I mean by this is maybe you have a HSM, or maybe you have some other embedded device, or maybe you have a regular server, but it doesn't actually have an IP address. It can't connect to the internet. It only has one little line of communication out to maybe it's a regular computer, or maybe it's some other computer, maybe it's some other server, maybe it's over serial, maybe it's over USB, and you feed all of the kind of communication with your peers over that line, and this allows you to have a device where the only thing it can communicate with to the world is over Lightning protocol to Lightning peers. It can't get hacked via some other means, and maybe it's physically secured as well. So this is ideal. Of course, this is kind of similar to how you might imagine a ledger or a Trezor or a hardware wallet integrating Lightning. You run the node effectively on the device, but it kind of communicates to peers over whatever interface it has, right? So this is the reason why Rust Lightning, again, doesn't make the actual TCP socket calls for you. It just tells you, here's bytes, please send it to this peer, or accepts incoming bytes from a peer. So it's very easy to wrap around a TCP socket, but you still have this kind of flexibility to be able to do other crazy integration work. Of course, this kind of sidesteps the issue of how do you monitor the chain, right? One of the key aspects of the Lightning security model is you have to have something that's always monitoring the chain. And so you can't just completely move over to something like a ledger or Trezor or hardware wallet because it's not constantly online and it doesn't constantly get chain updates. So if it's offline for a while, that's problematic. And of course, this is even worse because there are some cases in Lightning where maybe you have a pending HTLC, but your counterparty went offline, and in order to claim that HTLC, you need to go ahead and clear the chain before some timeout. That's even worse because you have to not only be monitoring the chain on like kind of long time periods, but you might have a specific time where you need to broadcast this update if you haven't been able to get in touch with your peer in some time. So in Rust Lightning, we try to get around this a little bit. We don't actually kind of natively do this for you, but one key approach that you might imagine taking is if you have this kind of hardware wallet or you have some device, you can have kind of pseudo-trusted watchtowers or trusted, I'm using the term watchtower overloaded a little bit here. It's kind of a trusted other half of your node. And you can send it an encrypted copy of the data it needs to monitor for, and it can sign that data, send it back to you, and say, yes, I've received it, I've updated it. And then you're still not necessarily needing to trust the computer in between, the like online computer, but you need to trust that that other device is actively monitoring the chain and gets updates. This is still kind of nice because you can imagine if you're really going down the rabbit hole of running some crazy high assurance Lightning node, maybe you have multiple copies of this kind of server, you have multiple things watching the chain for you in different geographic regions, and so you need to be able to take this data that it needs to watch for, send it to multiple servers, get sign off from all those servers, and then actually make progress on the channel. So Rust Lightning supports, again, it kind of supports this like pausing the channel temporarily until you've updated the watching stuff, the chain monitor, and then it'll continue. So those are the kind of two key use cases that are supported in Rust Lightning. But I want to talk a little bit briefly about some of the stuff that we've been working on in terms of testing and different approaches that we've taken from existing nodes that have kind of been enabled somewhat on accident by just the structure of the library. So this wasn't something that I kind of had as a goal in mind going in, but it turns out just because this library is flexible, it doesn't have a runtime, it doesn't have any syscalls, and so you don't have to do a bunch of setup work, it means we can run really great tests that literally can stand up 10 nodes in the same process just by making like 4 function calls. We don't have to go actually create daemons and like wipe things on disk and move things around, anything like that. So it has enabled us to write really fast, great tests all over the place. And also, of course, because we have this interface, like I mentioned, of getting messages and being able to handle those messages manually to send between peers, we can also reorder those messages. We can delay them and deliver them in specific orders, just really easily, just by changing, by moving lines of code around, instead of having to actually sit in the middle of a TCP socket and like hack up our daemon or have a bunch of testing code in the middle of our production code. We've also played a lot with fuzzing, or I guess I've played a lot with fuzzing in Rust Lightning. We have, obviously, fuzzers for all our message deserializers and stuff like that. For those of you who aren't familiar, fuzzing has been incredibly useful across the software world, but mostly for finding vulnerabilities in things like decompressors, image decoders, message deserializers, that kind of thing. And what it does is you write a program that takes as input some arbitrary string of bytes, and you do something with those bytes, and the fuzzer tries to make you crash, right? So if you have some image decoder or decompressor, oftentimes it'll find a bug where you use too much memory, you have an out-of-memory condition, and you have a DOS vulnerability there. Or maybe it'll find a bug where you have some buffer overflow, something like that, or whatever, depending on the language you're writing in. And fuzzers have been amazing. You can go look up all of the various CVEs and vulnerabilities they found. So we've been playing a lot with them in Rust Lightning. And we have the standard ones of just make sure all of our message deserializers don't crash or don't use infinite memory. But we also have some that allow nodes to do completely arbitrary things. So we have one fuzz target which runs a full node and can receive bytes on the wire. This allows you to literally do anything that another node could do to you, possibly, in a fuzzing environment where the fuzzer is trying to creatively crash your program and comes up with different inputs that might exercise different code paths. Fuzzers aren't that efficient, as you might imagine. They're just shoving in random bytes. They're much smarter than shoving in random bytes, but it is still shoving in random bytes. And so when you have these very large messages, they're fairly slow, and you don't have great code coverage. There's some new research on how to do fuzzing with a technique called taint tracking. If you're interested, you should go Google this. It's actually incredibly fascinating and is a great tool for building high assurance software. And we are exploring that a little bit in Rust Lightning, but we haven't gotten that far. We also have a more recent fuzz target, which tests for consistency of the protocol. So we can actually write little short snippets that allow the fuzzer to essentially write new test cases for us. The fuzzer can reorder the delivery of messages so that it simulates the speed of light. It can send payments, receive payments, things like that. And its goal then is to find inconsistencies in the state machine of our channel. Right? So you have two channels, on both sides of a node. You have a channel and you have two nodes. And your goal is to try to find a way to get the two nodes into some different state, because they shouldn't be able to. They're sending messages to each other. But if they somehow end up disagreeing about what the current state is, that's clearly a bug in our state machine. It's probably exploitable, because there's probably some case where we're forgetting about an HTLC or some funds. And this has been incredibly useful. We've maybe copied 20 test cases out of this fuzzer into our regular test suite and found a number of bugs, especially in our channel pausing stuff. So there's a lot of really exciting work that we've been able to do in fuzzing in Rust Lightning, in addition to just standard unit tests and standard protocol tests. One final thing I wanted to mention, for those of you who are interested in testing, the Rust ecosystem generally is, because it's a lot of engineers building often high assurance software, one thing that Rust has good tooling for, or that there are good libraries for in Rust that don't exist in most other languages, is a technique called mutation testing, where your goal is to kind of test your tests by modifying the actual software and making sure that your tests fail. Right? So if you take your software and you flip some if conditions, or you change some default initialization of some variables, your test should be able to catch that. Otherwise, you don't have good test coverage. And this is much more effective than just looking at kind of standard branch coverage or standard coverage analysis of your code, and can find a lot more details that you might have missed in testing and things that you should add tests for. So this is future work that we'd like to do on Rust Lightning. If you're interested in writing really cool state-of-the-art testing, come talk to me. Would love contributors. So with that, I was told I have to mention that Chaincode is running another residency program. We've had great success with these in the past. Most of the people end up getting a job somewhere in the space. But if you are really interested in Bitcoin and want to get really deep into the nitty-gritty of protocol engineering in both Bitcoin and how everything works and how people think about it, and Lightning and other stuff, you should apply. It's residency.chaincode.com. It's about 2 weeks of kind of intensive course-ish work, where there'll be a ton of talks by great speakers, me and some of the other Chaincode folks, and we have people coming into town just to speak to you. And then we're going to do it a little bit differently this time, and there's going to be a bunch of project time, so you can hang out in New York with us, with some great mentors. Some of the smartest people in the Bitcoin ecosystem will help you with whatever project you want to work on, whether it's Rust Lightning or BetterHash or contributing to Bitcoin Core or other Lightning implementations or whatever cool project you want to do. You can come hang out with brilliant people and do that.
Awesome. Thanks, Matt. We might have time for a question if anybody wants to jump in. Got time for one question. Jimmy, come on up.
I'm wondering about all of the upgrades coming up in SegWit version 1 and how that will change Lightning. How are you planning to upgrade the Rust library to handle all of the changes that are upcoming with,
Yeah, so I mean, with Rust Lightning kind of not being production yet, it means we can just not bother supporting old school stuff. And especially, even ignoring SegWit version 1 with the Lightning 1.1 changes, some of those changes I want to have in in Rust Lightning and support it on the network before anyone starts using Rust Lightning in production, because it'll simplify a lot of stuff about interfacing and making sure that it's really easy to use Rust Lightning and doesn't have fee disagreements. But yeah, also, obviously, the L2 and whatnot will hopefully make watchtowers orders of magnitude simpler, and we can just throw out old code because no one's using it yet.
Awesome. Thanks, Matt. All right.